So let's take a look at just exactly what L'Hopital's rule is, and then we'll work through some examples. Now let f and g be functions that are differentiable on some open interval a to b containing c except possibly at c. Now assume that f prime of x is non-zero for all x in a to b except for, again, at possibly at c. If the limit as x approaches c of f of x over g of x produces an indeterminate form, that means something in the form 0 over 0, infinity over infinity, then the limit as x approaches c of f of x is equal to the limit as x approaches c of f prime of x over g prime of x, provided the limit exists or is infinite. Now, what this is really saying right here is if I have a function of this form, that g of x has to be non-zero throughout this interval except at c. If it was 0 everywhere, then we won't really have much of a function. I mean, it'd be undefined over this large interval, so why are we even thinking about limits to begin with? That wouldn't make any sense. So I have something that as like in this case, when x approaches c, I get a situation where I end up with 0 in the denominator and 0 in the numerator, or infinity in the denominator and infinity in the numerator. That gives me my indeterminate form. Now to deal with this, I can simply take the limit of the numerator divided by the limit of the denominator. This is not the quotient rule. Okay, this is not the quotient rule. This is truly simply the derivative of the numerator divided by the derivative of the denominator. Now, once we do this and we take this limit and it's infinite, then we know that the original limit was also infinite. So we went from an indeterminate form to determine that the limit was actually infinite. Or if the limit exists meaning that it goes to some real number, then we know the original limit went to that real number. Now, you can apply L'Hopital rules for one-sided limits and limits at infinity. So you can use those, or use L'Hopital's rule also in those situations. So let's take a look at the example I did a few moments ago. I want to take a look at the limit as x goes to 1 of 2x squared minus 2 over x minus 1. Now, as I evaluate this at x equals 1, I ended up with 0 over 0, which is an indeterminate form. So what I'm going to say is that this limit is equal to, and I typically use the notation LH over top of it, which tells me based on the L'Hopital's rule, that's how I went from here to what I'm about to do, that this limit is equal to the limit as x goes to 1 of the derivative of this, which is 4x, divided by the derivative of the denominator, which is 1. See, that's just the limit as x goes to 1 of 4x, which is equal to 4, which is what I said it was in that previous example when I worked it out by factoring and canceling out. So it's the same limit. It's just much quicker. So L'Hopital's rule is an extremely powerful rule to use, but you need to make sure that these conditions are in fact satisfied, that you have continuous functions except possibly at c, what you're trying to evaluate at, and also that when you evaluate it at c, you're going to end up with a indeterminate form. Okay? If you don't get an indeterminate form, don't apply L'Hopital's rule. L'Hopital's rule only applies to indeterminate forms.